All right, students, if you take your science book and turn to page 376, and we're going to start or continue on with our chapter in the lesson in electronics, cover some things today that will help us as we look at the advancements made through this use then of the vacuum tube. And we're going to talk about the vacuum tube diode. We'll start out with that. So if you got your book there, something to underline with, would be good for you to have that there with you. And so as you notice on page 376, we have the term that's called thermionic emission. And we'll start out with Thomas Edison. What Thomas Edison did a lot of things, a lot of experiments. Of course, you know, if you think of the name Thomas Edison, probably one of the first things that comes to mind is a light bulb. And he did hundreds of experiments to get that light bulb then to emit the heat that emits the light. He even used, I understand, and some research, he even used a string that he soaked in salt water and as a filament, and he used that as a filament to get the electrons to run across, and it did. Of course, it heat up, it would burn the string up, and that didn't last very long. He used hundreds, I believe, hundreds of experiments to get what we now use as a tungsten filament to be able to transfer those electrons. But he had hundreds of different experiments that he did. A couple of them, one in particular with carbon, and with carbon, of course, you know that from carbon, of course, we use coal, and when you use coal for energy, it emits this black smoke-looking thing we call soot. So if you look with me, we'll read about this a little bit here on page 376. He says under thermionic emission, while experimenting with prototype incandescent lamp 1875, Thomas Edison then ran into a problem. He had removed all the air from the bulb to keep the filament from burning up, but after the bulb had been burning for a while, the inside of the glass became coated with black soot. And then, of course, he then would try to figure out a way to get rid of that black soot, because then the light would become, you would be able to see the light coming through as that soot built up in there. So what he did, if you look at the illustration at the top right-hand corner, page 376, what he did is he attached a metal plate. I've got actually my own drawing here of this. Of course, the one in the book's a lot better, but if you look here, let me get on this side. If you look here, then you see we have the bulb, and then you have the two electrodes, you have the filament in between, and then what Thomas Edison did is he attached this plate to a metal plate to the inside of the glass, had a positive charge attached to it, and of course the E stands for electrons, negative charge, as they're inside the bulb, and then those electrons then were attracted to the plate, and he would have them run out that wire that is indicated here. And as you see up there, he started out with a wire that was attached to this outside of the area here. And what he was hoping to do was to attract those electrons that are in the soot and attract the soot to the side of the bulb there, and so light could continue to come through. Of course, that didn't work, but he had tried that, but he'd come up with something then in this idea of this thermionic emission. As I've got up here, I've got the term here, then I've got therm equals heat, and then ionic stands for ions, which we've talked about in previous chapters, and those are charges. So you have heat charges in that bulb. That's why it's called thermionic emission. And he came up with this and used that. He really wasn't, that wasn't what he was trying to do, but he's trying to get rid of the soot by attracting those electrons with that plate. And as you see in your illustration there, it goes the charge goes up. The electrons are in the middle, and then you see as they shoot over across the bulb here to that plate. And he came up with this thermal ionic emission by accident, really, in trying to get these electrons that were causing the soot to move. And so he came up with that. Edison did that. And then we want to talk about, there's about 3 people we'll talk about today in our lesson. Second one is Fleming. If you look over then to page 377, we'll talk about him for just a minute. Ambrose Fleming. And what he did is he took what Edison did and took it a little bit further, as scientists will do. And he came up with, if you'll see at the top left-hand corner, what is called Fleming's valve. Now, if you look at that picture, right, and there, a Fleming's valve, and you turn over and look at the picture that's on page 376, and and compare them together, one thing you'll notice, and this is the great difference that's there, is the fact that the electrons, or the electrodes, are a lot closer together in the Fleming valve. And that's what Fleming came up with, and he condensed it down to a short area, which does several things. One, you don't need as much voltage then to cause those electrons to move as you would in the thermal-ionic emission bulb. There's a greater distance, so you need more voltage, more power to move those electrons. In the Fleming valve, closer together, you don't need as much power, which means you save energy, which means ultimately that you save money. And so here is the Fleming valve then, making it smaller, more compact, more efficient, and able to be used in more things because it's not as big an apparatus as the emission bulb is. And so if you'll notice there, you can see clearly that it's the 2 electrodes are a lot closer. And that's the main difference between these two valves, the Fleming valve and the emission bulb of Edison's. And that gives us a great deal of things we can work with. Notice there, if you have the anode electrode, you have the cathode electrode, as you do in all things, all bulbs there, and then you have the current that goes through it, and then there's a filament. There's a movement of back and forth then of these different all the electrons that are going back and forth. And so Fleming kind of took it a step further. He took it a step further, and it allowed then the electrons to move in one direction, of course. That's what we're after. And he came up with that, and the ability to reduce the voltage, right? And then the diode causes that current to go back and forth. Then the next scientist, DeForest, he's the last one we'll talk about today. He came up with he took that a little bit further, and he had said, look, there's got to be a way that we can still reduce that voltage, where it doesn't need that much voltage to get those electrons to jump from one electrode to the other. And so he, as you look at page 377, it says vacuum tube, the triode. That's what he's responsible for. Let's read a little bit here. It says in 1906, that's 2 years after Fleming came up with the Fleming valve, he invented after Fleming invented the diode, an American inventor, Lee DeForest, modified it by inserting a wire grid between the cathode and the anode and of the diode tube. And because the addition of the grid gave it 3 electrodes instead of 2, the Forest vacuum tube is called a triode. Instead of just 2 electrodes, it has 3. And so what he's done, then what he did, if you'll look with me at the drawing I have up here, and also, of course, you can look at the right-hand side of that page and you can see his triode. But basically, what the setup is, you have on this side, you have the plus side, then you have negative side, plus side being the anode, and then you have the cathode here. And what he did is he put a grid between these two. And he gave it just a slight positive charge there. So as the current comes up and goes through up into here, and then it gets to here, with this charge, it's attracted into this, but not enough to hold it. And it transfers and it shoots over to here. And that grid there then gave it an encouragement, if you will, to go ahead and move to the other side. Of course, and there's some results of that. It's kind of like this if you go shopping, and if you notice in your shopping department stores, they'll have clothes on this side and clothes on that side, but in the middle they'll have these little stands set up where they might be selling a product or just have some clothes hanging on it. And as you're walking down the aisle, they're trying to get you to encourage you to buy something by these little stands that are in the middle. And that will cause you to purchase something, or maybe not to purchase something, but they're there to encourage you. That's why they're placed right there where you walk. So it's the same way with this triode. This grid then is to encourage the electrons to pass on through there and to go to the other side, of course, to complete the current. And the idea then is that this is like a gateway or a gate that you could, for the electrons to pass through. With that grid there, the electrons can go through. You can open the gate and let the electrons go through. You can stop them from going through by changing that current, and then of course you can encourage the flow there. And so a lot of things that we get from this triode. Notice then in your book, if you'll take that, as we read on a little bit, notice on page 377, the second paragraph, the force realized that the triode is useful for more than just turning devices on and off. If a weak pulsating charge such as that induces a radio antenna by a distant radio broadcast is applied to the triode's grid, the much stronger current flowing from the cathode to the anode pulsates at precisely the same frequency. Thus, the triode, if you turn to the next page, 378, to be used as an amplifier device that can transform a weak signal into a much stronger signal. And so you can amplify your voice using this triode method. It amplifies with the current and helps to push that to an amplifier to give you a stronger and louder voice. Notice the italicized part here on page 378. It says, perhaps more importantly, triodes allowed the human voice to be transmitted and received by radio over a long distances. And so the triode, invention of the triode, and it opened another door for electronics to be more things than to be invented to use it. Notice the paragraph says the uses of the triode are not limited to radio. During the next 4 decades, scientists used triodes to construct television transmitters, receivers, radar, electronic computers. Although these devices have been refined as technology progressed, the forced invention of the triode made the modern electronic devices possible. So as we're heading towards this idea of as inventors keep improving the different things that have gone along, we're getting smaller parts. And you'll see this as we go. The size of the individual units become smaller. They become more powerful. The current that's needed to operate them becomes less, so we become more efficient. And so the idea is, that's the idea in producing things, is to get the cost down, to get the size more manageable, where we can actually hold it in our hands as we do our cell phone, and then to make it more efficient to run. So we'll stop there for today, and we'll be getting back with you at a later date, probably then tomorrow. Have a good rest of the day. Complete your work, and we'll see you then.